Okay, guys, welcome back. Okay, what we did last time, we talked about the Bayesian classifier, right? So I will go over this one very quick. I think we stopped in the middle, but yeah, let me go over this one again to make sure that we're on the same page. So what we try to do in this chapter, we'll try to present, to say, a different technique or approach in order to modeling probabilistic relationship between, the attribute set at the same time at the class label. So we're gonna we're gonna focus actually on something is called Bayesian classification, which again is a probabilistic approach based on is going to utilize the probability theory in order to make prediction. So something new. Okay, so it's based on Bayes theorem and also the conditional probability, which we covered them last time, which both of them is gonna be the fundamental concept, right? Which is going to help us in order to build, the model. We're going to see how can we do that, okay? So when you talk about the Bayesian classification, we need to look at the simple implementation of the Bayesian, classification or classifier action. So in this case, we're going to take a look to naive Bayes classifier, which again, probabilistic, let's say, framework, which help us in order to solve, the classification problems, which gonna relies on what's called, the concept of the conditional probability and the Bayes theorem. That's why we need to cover or look at them. If someone asks the question and said, why they call this one naive? Okay, because as we're gonna see here, which the one that we stopped on last time, is based on what? It's going to assume that the features are independent of each other. This the assumption, which is gonna help us in order to simplify the calculation, hence the name's naive. Okay, good. So when you talk about the classification, as we mentioned last time, the theorem, or let's say the basic or building blocks that we need to cover, we need to look at it's what's called the conditional probability and the Bayes theorem. Okay, when you talk about the conditional probability, that means in this case I need to compute the probability of y given x equal to what? The joint probability of x and y divided by marginal, let's say, probability, right? And I showed you last time how can you compute, the marginal probability, okay? Then either, it depends, by the way, what you try to, to calculate, whether the probability of event y is going to be occurred given the event x is, let's say, happened, or the probability of x, what's the probability of x is going to be happened if, or in the case, the event-wise occurred. Okay? So in this case, we can say the joint probability is going to be what? X and y is equal probability y given x times probability x, which equal at the same time the probability x given y times the probability of y, all right? Okay. Then we talk about the Bayes theorem, which help us in order to solve a lot of problems as we saw last time. I'll give you an example I gave it to you last time. So here it's equal, probability of y given x is equal to what? I'm going to substitute the joint probability x and y, okay, which this means in this case the event that to say, x equals specific value and y is equal other value, okay? So in this case, I'm going to substitute this one using what here? The probability of x given y times the probability of y, and that's what we did. Okay, and this is the marginal probability as we talked about last time, which help us in order to what? In this case, you're gonna perform, let's say, sum of the probability based on, let's say, specific random variable. So I will sum all the probability over, let's say, all the possible value of y, which is gonna help us in order to compute the probability of x. Okay, let me write, the Bayes theorem again here. Then we're gonna look at something. Try to explains in more details. Okay, so in this case we have what? We can see the probability, for example, of y given x, which equal here the probability of x given y times the probability of y divided by the probability of x, right? So we usually do what here? The probability of, let's say, y given x, we call this one, the posterior probability, right? And here the probability is so that means in this case the posterior probability of y given x, which in other words you can think about, it's the updated probability of y after I observe the, let's say, the variable x. Okay, And here, the probability, let's say, x given y here, let's write this one here, we call this one, let's say, the likelihood of observing x given that y is true. And here we have the probability of y. This means this is the prior probability, let's say, of y. This is before, whatever the probability of y, before I see what the value of x is. Then now, since you give me some value of x, now maybe it's going to be changing me the way that I'm thinking about the probability of y, how it's going to be calculated, right? So generally speaking, when you're using, the Bayes theorem for classification, which help us or involve, let's say, treating each attribute of the class label as a random variable, as that we did last time. We tried to, let's say, formalize, the classification problems, right? We talk about this one. Let me jump here. Yeah. So assume that in this case, x and y is going to be like two random variables. We assume last time x is going to be, let's say, they represent, the set of attributes, okay, or the attribute set, and y is going to be the class variable, right? So in this case, if you give me like any table, let's say, training data, so this part is going to be x, and this one is going to be y, okay? What attribute? Good. We assume here both of them is going to be the random variables, okay? And the value of x is going to be can have to say x1 up to xd. So we assume that we do have like a d attribute in this case, right? So the goal here, we try to what here? Given a data instance, if someone give you, let's say, given, let's say, x, what's my goal here is to predict. The goal is to predict, what is the value of y? So what's the value of y is going to be here? Okay? And you try to find the class y. Of course, I'm going to give you like, let's say, test data, right? Good. So the goal here, when you look at this one, so generally speaking, I'm trying to compute what? What is the probability of y given x, right? And I know the value of x is going to have, let's say, d values, right? D attributes. So in this case, I'm trying to compute the probability of y given, the probability of y given x has, for example, x1 up to xd, right? And now we try to write the formula using the Bayes theorem, which is going to try to help me to perform this, operation. Okay? Good. Let me jump here, I believe. Yeah. So how can you use the Bayes theorem in order to help me to perform the classification? So again, you try to compute the posterior probability of y given x1 up to xd, which the instance variable, using a Bayes theorem, and this is the formula how they're going to perform that, right? What we've said here, let me write this one because you need to find a way how to work with this one. So here, basically using the Bayes theorem here, I will try to write this one using the variable that we have. I'm trying to have the probability of y given x1 up to xd is equal to what? It's going to be the probability of x1 up to xd, okay, given y, times the probability of y divided by the probability of x, right? Which is going to be the marginal probability, right? This one, x1 up to xn, d, sorry. Okay? That's it. So far, so good, right? We are viewing, what we did last time, actually. Good. So my goal is try to what? Try to maximize the posterior here. I'm trying to find what's the highest value that makes this one to be maximized. Okay, because, for example, as we did last time, assume that we have a binary class label. Y either can be yes or no. So I need to make sure that which is the highest value of y, which maximizes this probability, all right? Which the probability of y equal yes given x, or the probability y is going to be no given the test instance, right? This one, if try to maximize this one, this is equivalent to what? Equivalent in order to choose the value of y that maximize what? The probability denominator here, right? Try to find the value of y that, let's say, maximize the probability of x1 given up to xd given y times the probability of y. Someone can say, how about the denominator? Denominator can be not related, or say depending on the y, so we treat this one as a constant. Okay? And the question that we start looking at last time, you can compute the probability of y. The problem here, how could you estimate, the probability of x1 up to xd, given y. So my question that I tried to solve last time, we tried to see how can we estimate the probability from x1 up to xd given y. To simplify the process, we can say the probability of x, and they use, to say bold x given y. How can we estimate this one? This is the one that we try to look at to see whether we have a different ways to perform that or not. Okay, good. I gave you an example last time. We're not going to go over this one right now. So if you give you a test, a record, for example, this is a value. See that you give you, the value of all the attributes, in X, say the features, then you expect for you to what? In order to try to find out what is the class label associated with this. And since we have, binary value for the class label, so I need to find the value, the highest value of y that would it be equal yes or no, given the data that we have. And to simplify the process, I didn't need to write, for example, the class label y equals specific value. I'm going to say the probability, the class label is going to be yes given x, and or no, which is going to be simplify the process. Okay. And now we're using the Bayes theorem. What we need to do here, since we have two different values of y, I'm going to try to compute the probability of y given x and the probability of y as yes given x, and compared with the probability of, the class label is going to be no, given the same instance. Then you try to make what? Which one is going to be higher? The probability, the highest probability, that means in this case, this is going to be my class label. Okay? And again, we'll try to see how can we estimate the probability of x given the class label. Either going to be yes or no. Okay? Good. So in order to do that, that's what I stopped on last time here. So we are going to look at, let's say, the Bayes classifier, naive Bayes, which help us in order to estimate the probability of x given y. Okay? But in order to do that, we need to do like some, let's say, assumptions, right? In order to try to, let's say, estimate this probability. Okay? So let me, So the first one here, I'm going to talk about something that's called conditional independence. Remember, we talked about the naive Bayes, classifier said we are going to assume that all the attributes, the features, are independent, which is not realistic in all the situations, right? Sometimes it can be independent. But this is to simplify the process. When you do that, this is going to help us in order to compute the probability of x given y. And we're going to look at to see how can you do that, okay? To see that, let's give you like, let's say, assume that we have, let me write this one different. Yeah, use this one to be much easier. This is one. So what we're going to do here, assume that we have two random variable x1 and x2, okay? And we have y, okay? I think three random variables. We say that, for example, the random variable x1, that's what I'm trying to say here, is conditional independent of, let's say, or conditionally independent of x2 given y. Let's say conditional on conditionally independent of x2 given y. Okay? F. There's a condition. I can claim, I can say, for example, x1 conditionally, let's say, independent of x2 given y, f. There's a condition. If the probable, if, for example, the probability of x1 given, let's say, x2 and y is equal to the probability of x1 given y alone. And that's what they're trying to say here. So we're going to say here the probability of x1 given x2 and y is equal to the probability x1 given y. So in this case, I can say x1 is independent or conditionally independent of x2 given the value of y. How can you do that? Okay, if I did that, if the value of x1 and x2 are independent given y, this is going to help us to simplify, the computation of the probability of x given y. How? Remember, x is going to have multiple values, many features, x1, x2, up to xd, right? Good. So this implies if I have this one, x1 is computational or conditional independent of x2 given y, that means in this case, this implies that when the condition on y, okay, the distribution of x1 is not influenced by the outcomes of x2. This indicating that x1 and x2 are conditional independent. So let's have an example, the same one that we did here, okay? So we assume here in this case, assume the relationship, say, between the arm length, we assume that it's going to be x1, and let's say reading skills x2. Initially, one might observe, for example, a correlation between longer arms and better reading skills. However, this correlation can be explained by another factor such as the age y. Okay, so when age is going to be taken into account, you can think, at the beginning, a younger child typically has a shorter arms and limited reading skills compared to the adult. But if we fix the age, okay, there may not be an apparent, let's say, relationship between the arm length and the reading skills. So they're not going to be independent. At the beginning, when we didn't fix, the age, yeah, they are independent, right? But when you, say, fix the age, we end up this, it's not clear for us to find a relationship, between the arm length and the reading skills. As a result, the arm length and the reading skills are considered, in this case, conditionally independent given age. And that's what we did, okay? Good. So now I can come up with another way to describe the conditional independence. I need to find a way to help me remember. My goal, just to remind you, we tried to find a way to help us to compute the probability x1 up to xd given y. That's my goal. So if I said all the values of x1 up to xd are independent, conditional independent, that's going to help us in order to find a way to perform the computation to solve it, or to find to solve it. Good. Or to find this, or calculate the probability. So another way to describe, the conditional, let's say, independent between x and y, okay, as we described here. I try to find another way to write this one, okay. I'm gonna say, in this case, I can try to use, the joint, conditional probability. So try to use, the probability of x1, x2 given y, okay? Which can be described as the following. I'm going to say the probability x1, x2 given y is going to equal to the probability, say, x1 given y times the probability of x2 given y. And we can prove it using this. If we given this one, we can write this one easily. We can find out how the probability x1, and x2 given y is going to equal to the probability x1 given y times the probability x2 given y. If I manage to use this one, so I can use this formula in order to help me, in order to write this one. So if I can use this one, I can write the probability x1 up to xd given y is going to be equal to the probability x1 given y times the probability x2 given y up to the probability of xd given y, which is going to simplify the process. So this expression that we talk about here illustrates, the joint conditional probability of x1 and x2 given, y, which can be decomposed, as we did here. The product of the conditional probability of x1, okay, and the, x2, consider, separately, right? Let's say, it's better to say conditioning on y, okay? Somebody gonna say, let me prove this one. How you did from here and end up we have this, okay? So we can write this one here. It's not required to prove this one, but at least we try to understand how we came up with this one. x2 given y is equal to what? What's the probability of x given y? Okay, it's gonna be the probability of, in this case, it's gonna be here x1, x2, and y, which is gonna be the joint probability divided by the probability of y, all right? The one in the condition is gonna be the one in the denominator. Good. So this is this one, yeah. If I say x1, x2, and let's say comma y, or the joint probability, and let me write this one in different way here. I didn't do anything. I didn't change anything, right? Then I can multiply or divide this one, or multiply with x2 comma y, and divide by x2 comma y. Can you do this one? Yeah, they cancel each other, so I didn't do anything here. Good. If you take a look at this part here, what is this? This is, the probability of x2 given y, right? And what's this term? This term here, if we use, this formula that we have here, so I can write this one as the following, right? Which will be the probability of x1 given y, which I mean the condition that we start with, right? So in this case, I can say the probability of x1 given y times the probability of x2 given y. If we assume the condition can be here, let's say conditionally independent given y, so in this case it's easier for us to decompose, I mean, let's say this probability into the product of the conditional probability of each, let's say, features given the class label y. Okay, this one can be written as something like this: the product I is equal 1 to d, and we have the bxi given y. And now we solve the problem that how can you compute the probability of x given y, right? If we can do that, then it's for us, you need to do what? We need to see how can you perform the computation, right? Or how can we use them? Good. And that's, I mean, to put everything together. So if we try to use a naive let's say, Bayes classifier, we need to do what here? We assume the class conditional probabilities is estimated by assuming that the attributes are conditional independent. That's why it's called naive. Good. Given the class table, of course. I always forget, I mean, I mentioned the class, given the class table must be, I mean, given here. This assumption of attribute independence allows us to simplify the joint probability calculation, as we're going to see it. You see, the probability x1 up to xd given yj, I use j to different parameter, probability x1 given yj times up to probability x2 given yj up to the probability xd given yj. And now we're going to look at the way, how can we compute this probability? This probability, for example, it depends on the feature type, right? Because here, since x1, x2 are all of them up to xd are independent, given the value of y, or variable y. So for each of them, in order to compute the probability of each feature, it depends on the data type of the feature. As we're going to see, I'll give you like two cases. I'm going to see how can we compute the probability, and the rest is going to be straightforward. Okay. And now, I need to make sure that, remember we talked about the denominator here. We said in order to perform, I mean, the class labels, I need to do what? I need to go back here. I need to make sure that the probability, for example, y given x, I know this one, yeah. The probability x given y times the probability of y should be maximized, right? I'm trying to find the highest value that maximizes this probability, right? I'm talking about the denominator here. Either going to use this formula, or you can write this one as we did in the slides here. It's going to be the probability of y. The product I is equal 1 to d. The probability of x I given yj. I guess I use yj. Okay, and I can use yj here. Yj, that means for each class. If it's j is equal 2, for example, in case we have y is equal yes or no, so j1 is going to be yes, then I need to compute this one for the probability of y equal yes, given x equal this one thing. Then after that, compute the same, do the same computation using the probability of y equal no, given x. Then see which one can be the highest, provide you with the highest value of probability, which is the value that we need to, I mean, to include. Okay. Oh, this is, I mean, the help you to compute the class labels. Again, it might be at the beginning someone gonna say, oh, we have a different techniques in order to perform the classification. Yes, it depends on the data type that we have, and it depends on the algorithms, okay? And each of them gonna have advantage and disadvantage, and this is a different way which help us in order to perform the classification. Okay, good. Now let's have an example and see how can you do that. Using examples is gonna help us in order to understand what's going on, okay? So let me try, for example, give you like a test data. X is going to be all the values found, for example, equal no, and the divorce and income equal 120. And I need to compute this case. Remember, in order to write, let me write the formula here. Then after that, to see what we need to compute actually. I wanted to do the following here. I need to compute, I mean, the probability of y given x, which is going to be the probability of x given y, divided by the probability of x times the probability of y, right? And that's the formula that we have. X is going to have multiple values, so which is going to be equal to the probability of x1 given, let me write this one, equal probability of y product I equal 1 to d for the probability of xi given y, okay, divided by the probability x. And that's what I need to compute. Yeah? This is my formula that we have. Since we have d features, yeah, good. Now I'm trying to find, I give you like the instance or data set, I just try to see how can I compute the probability of x given y, okay, for each feature. And I want to show you it depends on the data type that we have, okay? So in this case, if we give you like the value of x that contains, let's say, the refund equal no, okay, then we have the say divorce, let's say divorced, and we have income equal 100k. So in this case, if you try to write this formula here, this can be written as the following: the probability of y times the probability of example x, let's say refund equal no given y times the probability of example divorce given y times the probability of example income equal 120k given y, right? Divided by the probability of x. And that's what I need to compute. My job right now to see, for example, how can you compute each of them? For example, how can you compute this? And how can you compute this? And how can you compute this? And if you notice here, we have different data types, right? But we have, for example, continuous data type, maybe we have the categorical data type. So we're going to see how, based on the different data types, how can you compute this value? Once I know that, then it's going to be easy, right? Okay, I will do this one in case, in two cases, if y equal, I mean, yes or no. Sorry, yeah. I need to, before this computation, it depends two different values of y. That's why I use yj here in the previous step. So here, I'm going to say y equal yes, yes, yes. Then after that, perform the same computation using the value of y equal no, right? And see which one can be provide me with a high or the large probability. Good. Let's start step by step. First, let's do with the easy thing. Can you compute the probability of y? Usually you don't need to do that, by the way, all right? Because what we're gonna do here, if we try to compare, let's say, the probability of y equal yes, and the product of say I equal 1 to d, okay? In this case, we have up to 3, right? The probability of xi given y equal yes, and I will compare this one with the probability equal no, y equal no, okay, times the product I equal 1 to 3, since we have 3 features, and you need to compute the probability for each feature given the value of y equal no. So in this case, I don't need to have to compute the denominator, because the constant can be cancel each other, right? We use this one in order to perform normalization, make this probability should be within 0 and 1. Yeah. So anyway, so that's 1 and that's 2. I need to compare both of them. So that's why I don't care about the value of x. I'm looking for here what's the value of y equal, probability of y equal yes, probability of y equal no. Can I compute this one from the data? Yes, we'll start with a simple thing. So what's the probability of y equal yes? I have 10 items, I was in instance in the training data, and 3 of them are going to be equal to what? Yes, right? So 3 are the frequency, right? The data item instance that have what? The class label equal yes, and here the class or fraction of the instance of class y equal to no, which is going to be 7 divided by 10. So it's easy, right? I can compute the probability of y. Simply, I will write this one here. Y equal yes equal 3 over 10, because we need to use this one later. And y equal no, I can say this is going to be 7 over 10. Good. This is the values that we have. Now let's say here, as I mentioned here, it depends on the data type or the feature that you have. For each data type, we have a different way to perform, let's say, or compute, let's say, I mean, the probability of x given has equal specific value given y. So for example, I will look at, for example, first for, let's say, marital status, or let's say for the, later they're going to look at the taxable income and see how to compute that. Okay. So, how to estimate the conditional probability for categorical attributes? If you have a categorical attribute, okay, for example, in this case, you need to do what? You need to estimate, for example, the probability of x, okay, let's say equal specific value given the class label y. So in this case, it might be the probability of x, I didn't write this one. I should write, the attribute, right? Which in this case, the marital stats, for example, I tried to compute the probability, for example, let's say marital status equal, in this case, divorce, given y equal yes and no, right? We have two options, right? You say y equal no, then I need to compute the probability, for example, marital status equal divorce, given, I'm gonna say no, yes, just to simplify the process, and I'm gonna say no, right? And that's what you try to do here. This one equal yes and y equal no. How can you compute this one? If you have a categorical data, so we can do the simple formula here. So if we give you the probability of x equals specific value, and x is feature is categorical data type, given y is equal to what? Can be counted as the following. You use this formula, nc divided by c. What's n? It's computed or estimated according to the fraction of the training instance in the class y, where xi takes a particular categorical value x, c. So that means in this case, I'm gonna, this n. N is gonna be here is the number of training instance belongs to the class y. Let's say number of training instance belongs to class y. Actually, instance belongs to class y. Okay? How many training instances that has the class label either can be yes or no, right? So yes, we have only 7. No, we have, yes, we have only 3 instances. No, we have only 7 instances they have the class label. So among of them, how many of them has the specific value, let's say C? Or out of them, NC number of instances have, let's say here, number of instances, say, have X equals C, okay? Let's try to use this formula and see how can you use that. And now it's easy. See, take a look here. What the stats equal merit and the class table equal no. The total number, let's say, of training instance belongs to the class y equal no here. We have 7. 3, 4, 5, 6, 7, right? Among of 7, how many of them has, let's say, the stats equal, let's say, merit or divorce? In our example, we said either merit. Let's say merit among from the no, you see how many merit? 1, 2, 3, and 4. So it's going to be 4 divided by 7. Divorce, for example, and no, check from how many of them? Here we're going to see nothing, or we have 1 only, all right? So there'll be 1 divided by 7. Sometimes that's fine if you have the probability equal to 0, which that's the problem that we're going to look at later, and we're going to see we do have like a small fix to it, okay? So first, let's try to commit the refund equal yes, given the class label equal yes. So again, in this case, when you work with a refund, it's yes or no, right? And in this case, I mean, you can use the same formula, works fine, or you can see how many refund equal yes, given the class label equal to yes here. So in this case, the class label equal to yes, we have 1, 2, 3. Okay, among of them, how many of them get a refund equal to 0? I don't have none, so it can be 0. So, make sense? So this, the only thing you need to look at with the Bayes theorem, we have assumption to simplify the process. All these features are independent, conditionally independent given y, which simplify the process, which allow me to write the formula as this. And now for each of them, I need to commute each value, the probability for each feature given the class table. It depends on the data type of each feature, right? And that's what we did here. So that's what we assume, that if the data can be categorical attribute, how can you estimate the conditional probability? Now the question here, how could you estimate, let's say, the conditional probability for the continuous attribute? Now we have a continuous attribute, which in this case, the income, right? It's continuous attribute, right? I cannot use the same formula that you use a categorical attribute, right? So we have another way to perform that. So that's what we're gonna look at. We have a different ways. The simple thing, we can use discretization, okay? Or discrete, the value, which in this case, you're gonna do what? Partition the data into range, into bins, and you can specify or assign, say, discrete value, all right, for each of them. Or we're going to do something different, which I mean, we didn't do this one before, right? We can use what is called, I mean, the probability density estimation, which is the one that we're going to use here. Here we have an assumption. We assume that all the attributes, or this attribute actually, for example, the income, that is, I mean, the continuous attributes, follow, I mean, the normal distribution, for example, okay? So I can use, in this case, I mean, the training data, within this case, this data here, I can use the training data in order to try to what? To estimate the parameter of the normal distribution. What the parameter that we need to estimate in the normal distribution? I need to find the mu, and I need to find, I mean, the standard deviation, right? I need to, right? That's what I'm looking for. The sigma and the mu. If I know these values, estimate these values from the instance or data instance or the training data, so it's easy for me in order to estimate or find out, I mean, the probability associated with that, I mean, attribute, right? So once I know the probability distribution, now I can use in order to estimate the conditional probability xi given y. Again, for the categorical attribute, and C divided by C. For this continuous attribute, I'm going to use, I mean, the estimate that using the probability density, I mean, estimation. So let me write the formula here, okay? And this is the formula that we need to use here. And we need to have what? I will write two different formulas, which is going to help us in order to estimate that. So in this case, if we assume that x, say, is, I'm going to use x, okay? I want to say xi, whatever attribute that we have, is continuous attribute. Okay? So in this case, and I need to do what? I need to compute, I mean, the probability here. So I need to compute, for example, the probability of xi given y. Okay? Which equivalent, or you can say equal. I can't say equal, but because it's estimation, we're going to say equivalent. Okay? 1 over what? I mean, we have many ways to write this formula, right? I can say it can be sigma square root 2 to say by, right? Or you can say, or you can use, I mean, this is the same, right? By sigma square. Both of them are equivalent, right? Okay, times e to the power, for example, minus xi minus mu divided by 2 sigma square, and all of them gonna be, I mean, sorry, this is gonna be square, the top. Right? And this is the formula that we have. The xi is gonna be the value of the attribute, I mean, that try to estimate. And mu and the sigma, and gonna be able to say the mean and the standard deviation, I mean, of the attribute I for the class y. Okay? How can you do that? First, how can you estimate to compute the mean? The mean is going to be mu equal to what here? 1 over the n, summation to say I equal 1 up to n, and n is going to be number of instances that I have, right? Okay? That for the attribute xi. Okay? Again, what's n here? It's going to be, let me write this one, it's going to be the number, n is the number of, you say, instance, or let's say in the training set, okay, data for class y. If y equal yes, that means in our case 3, right? If class y equal no, that means we have a 7. Among of 7, so it depends on the value, and this is xi. The sigma, or the, let's say the standard deviation, equal to what here in this case? I do have the formula, right? Yeah. I can write this one as, you need to write this one, I guess. 1 over n minus 1, right? Summation I equal 1 to n, and you can say xi minus x bar square, and x bar is going to be the mu value. So this is a formula that we can use in order to compute, I mean, the sigma. Okay. Once I have this value, if you try, I'm not going to go over this one, but yeah, I did the calculation just to confirm the numbers that you have. So in this case, we have what? If you try to sum the number, assume that y equal to, yes, no, that means in this case you have to what? 125. Those are the values that you need to, I mean, the sum to compute the mu. 125 plus 100 plus let's say 70 plus 120. Remove the k, okay? plus 60 plus 220 plus 75 divided by 7. So it's going to be here in this case 110. And you try to compute, the sample variance, by the way. Okay. So in this case, I need to do what in this case? 1 over n minus 1, sum I equal 1 to n xi minus mu square, and you take, the square root for the whole value. So in this case, using the value of mu here, in order to perform the sample variance, you did this one the first day, I believe you work with the statistics. Then after that, we have the value of sample variance going to be 2,975. This is square, so I need to compute this one, plug the numbers here. And this is, if you give you like a specific value for the income, what you need to do here, just give me whatever the value of x, so I can plug the numbers in order to compute, the probability. Okay, so it depends, by the way, what the value here, it depends on the instance that I have, right? So the example we said the income is equal 120. So you can perform the parameter with the yes or no, and now waiting what the actual value of x. Plug the value of x and plug that in the formula, and there's going to be straightforward. Okay, good. Now I put what? Everything together. I try to have what? I need to apply the Bayes classifier. Okay, so I give you like a data. I put this data instance. Okay, and now we have what? We try to apply the naive Bayes classifier. If you take a look here, I wrote this one here actually. Yeah. Remember, that's the way how to compute the naive Bayes here. You need to compute the probability, for example, y equal yes, product I equal 1 to 3, pxi given y equal yes. Then you know how to compute each feature. It depends on the data type, as we did here. Then after that, you have to do the same thing, but now we need to perform the computation based on the other class label for the y. Then you need to compare them. And that's what we did. So what we did here, we tried to compare or compute all the possible probability of xi, and all the possible probability given y equal yes and no. Then after that, perform the computation. And that's what we did here. I put the data here. So the probability of find this xi given y yes and no. Check the value. You know how to compute that. 3 divided by 7, categorical attribute. You can think about this one. Let's have one example here. For example, the marital stats equal single given the class label equal yes. Think about what this categorical feature. So I have nc divided by n. So n equal in this case equal to 3. Only you have 3 instances has the class label equal to yes. And we have what the value of n. nc in this case. How many among of them has the marital stats value equal to single? We have 1. This yes, right? On the yes we have 0. We have only 1, 2. So it's gonna be 2 over 3. Okay, so this one is straightforward. Do you have any question related to this slide, especially for the first part? How to compute the conditional probability for each feature, especially if the feature is going to be categorical data type? Oh, you are sad because are you happy today because today is the last lecture, or you are sad? I think you are sad, right? Because you are not going to hear my voice anymore. Or you are happy. It's yes or no, right? So you have to compute the probability and see which one is going to be maximized the class label, whether you're going to be happy or not. So quiet at your side, guys. Oh, yeah. Yeah, that's what we're going to do right now. But right now, I just compute all the computation, and that's what we did. You see, that's what we're going to see here. And that's the answer to your question. That's what we did here. The probability x, see, let me write this one. I'll go back here. And that's what we did here. That's the actual formula here. Let me write this one in a nice way, okay? So we try to do what? Probability of y equal yes, given x, equal to what? Compute the probability of y equal yes. Right? Product I is equal 1 to 3. The probability of xi given y equal yes. Divide by the probability x. I will ignore this one because it's going to be constant. Okay? Good. Then after that, I need to do what? The probability of y equal no. given x equal the probability of y equal no times the product I equal to 1, as you said, yeah, because it's independent, probability of xi given y equal no. This actually probability divided by probability x, but I'm not going to look at this one. Compute this value and this one, see which one going to be has the highest probability. Then in this case, this is the one going to be the class table. So yes, we're going to split the attribute, or I prefer to say decompose, right? Yeah. Okay? And for each of them, now, how I compute, for example, the probability of x1 given y, let's say yes, then the probability of x2 given yes, and the same one time, I need to compute x1 given the class table equal no, and the probability x2 given the class table no, since we have three attributes, and the probability x3, the class table yes, and the probability x3, the class table no. Okay, so all the possible combination here. And now it depends what the x1, numerical data type, categorical. Oh, nc divided by n. What if x2 is not numerical? I would say categorical. For example, what if it's going to be continuous attribute? Oh, now we're going to use, what we did, when using, the probability density estimation as we did before. Make sense? So what we did in this slide, we just put everything here. We said we tried to do all the possible combinations, and that's what we feel for all the value of x, I, yes, no, yes, no, yes, no, yes, no. And here in the top, all of them. So you see the refund and marital stats, both of them are categorical data. The only one is going to be here is like continuous. Oh, we have different way. Now we're going to see if the class label equal no, I need to compute the sample mean and the sample variance. I need to have the parameter, because why I need to have the parameter, let me write the formula. That's the formula that we're going to use here. If they're going to be no or yes, say, for example, assume that x3 is, let's say, continuous. Attribute. So in this case, I need to compute what? I need to compute the mean and, let's say, the sample mean and sample variance if the class label for y equal yes and for y equal no. I need to have what? The sample mean, and I need to compute the sample, let's say, variance. How I compute that? This is the formula that we have, right? 1 over summation I equal 1 to n xi, and this one 1 over n minus 1. The formula that I gave it to you last, here, right? And this is the formula that you have to compute that. If you write this one, this one is going to be, I use the square root, or say, yeah. I'm going to use, sample variance, okay, not the standard deviation. It's going to be 1 over, let's say, n minus 1, okay? And the summation I equal 1 to n xi minus, let's say, mu square. And this is the formula that we have, right? And you have to do this one for the value of y equal no. The same thing, you have the sample mean and the variance. In the slide here, we did the mean for y equal yes. No, actually. That's what we did. Yeah, we did for y equal to no. You need to have the parameter. So each of them, you have the mu and sigma square. Once you compute the mu and sigma square, you have to plug this one into the formula based on the value of x. So in this case, the probability of x equal, let's say, x3, given the y, it might be yes. Or here, the probability of x equal x3, given the class table equal no. So in no, I need to use, the value of no, corresponding to the parameter here. And I need to plug this one into what? To 1, let's say, 2 pi sigma square, e minus xi minus mu, this square, divided by, let's say, 2 sigma square, okay? And this is the formula. And what's the value of, let's say, mu and sigma square or variance? It depends whether y equal yes or no, because you have the parameter here. And you just plug the numbers, and the rest can be straightforward. Yeah. Exactly. Exactly, yeah. Because usually, remember, we talk about the classification, what we try to do here, classification. I give you like a data set, right? You're going to have like a data set, right? And you need to do what? We are not going to build actually model here. But what we're going to do here, there's a different way, right? So in this case, it's not like decision tree. You have to build the model, then you can apply this one later. This, as long as the training data is there, I'm waiting until you give me like a test data. If you give me test instance, I'm going to perform some computation in order to try to estimate, the probable, the class label based on the probability to say what is going to be the class label for the X in this case. Make sense? So we have to go through this one. So right now here, you do have what? We have the training set here, okay? It's ready. And now all the waiting. When someone give you like this value, for example, I need to find out what is the class label for the test set or instance in this case. Oh, in this case, I start doing the computation. Start perform. I'm going to use the name to say Bayes classifier. In this case, it requires for me to perform the conditional probability, right? Probability of y given x equal the probability x given y times the probability y divided by the probability x. I don't know how to compute the probability x given y, so that's why we have to perform the Bayes theorem and Bayes theorem classifier, which require me to do all this computation. At the end, right now, since I do have two possible class labels, I will perform this one to two class labels, whether y equal yes and y equal no. And that's what we did. I just compute the value x given no, class label no, and the x given class given yes. Then this value that I have a problem, I will multiply this one with the probability of class label equal no, and this one multiply with the probability of class label equal yes, right? Then I try to compare them, and that's what we did here. So in this case, what we're gonna do here, we compute this. Okay, we have computed this part, and we did this one with yes or no. Do you agree with me or not? For each test instance, then after that, I will multiply this one with probability of y equal yes, compared if I multiply this when the class label equal no with the probability of the class label equal no. This is the prior knowledge, and somehow that means the posterior knowledge can be changed. Because now, that's what I have at the beginning, probability of the class label can be equal to yes, but I have like extra knowledge, right? That's gonna change, my overall probability. So which one, the highest one, it one gonna be the class label of this class. And that's what we did here. If you see here, I show this only portion that x given no, yes, and the one that I highlighted in the red in the paper, then I will multiply this one using what? The probability of y equal no, compared to the probability of y equal yes. We found out that the probability of what? This part, if the class label equal no, is greater than if the class label equal yes. So what does that mean in this case? The probability of class label equal no given x is greater than probability of class label equal yes given x. So in this case, the class label of this class can be equal to no. Then now, if you give me another instance, I will do the same computation. Okay? Mostly, this one is not going to be changed. Okay, so the one in the left is not going to be changed because this one going to work with every single instance. Yes or no? Yes, because those are this column or the left here is based on the training data set. You can't perform this computation and waiting. Give me an instance value. Oh, now I need to perform this computation here, right? Of course, one thing you need to change if you try to compute the probability, for example, x3 or whatever the income, based on value of the income here. Because when you say the income is 120, so this part is going to be changed, right? It's not going to be the same. For example, you try to find the class label if the income is equal 200K. Oh, this one might be changed. It might be the class label in this case is going to be no. Yes, it's not no, right? But the left in the column, or there, this column, the pre-computation based on training data is going to be the same. It's interesting, right? Because right now, at the end of this class, you're going to see that we have a different way how to perform the classification. Each of them based on different knowledge. I would say, yeah. Okay. I need to add the lab, okay? So, by the way, in the lab, I'm not going to ask you a question about the lab in the final exam. So the lab's just to make sure that you try to practice, try to apply whatever we cover in the class. Okay? So the most important thing, when you work with the data mining, at least when you use any technique or methodology, you know the background, you know the definition, you know that why we're going to use and how it works. Good. Okay. Another thing here, the good thing using the name Bayes, classifier, we can do the decision with the partial information about the attributes in the test record. For example, now the test record can be refund, marital stats, and taxable income, right? I provide you with the value for all three attributes. Can I perform or come up with a classification or the class label if I give you like a partial information? For example, if I give you only the taxable income, or I give you the marital stats or the refund, are you still being able to use this technique to perform the classification or not? The answer, yes, which is a good advantage here. So assume that in this case, I give you like, for example, only the marital stats is default, only. We have only value of x1, only value of x, not three values. Can you do that? Yes. So we're gonna apply the same formula, right? What we're gonna do here, this is the formula here, we're gonna work with this, the probability, the class name is gonna be as given, say, the instance, or the test data, in this case, only one attribute. The probability, for example, y equal yes, multiply the probability of x equal default, given the class table equal yes, divided by the probability of default, all right? The denominator in this case can be ignored completely. You don't need to see how to compute that, right? Although you can compute that, right? By what? By sum all the probability based on all the possible, say, class labels, all the value of y. But we don't need it because we can cancel this one. The most important thing, I need to compare, the denominator. And before the same thing with the class label equal no. And now we're going to see that, for example, which one can be higher than, right? Another thing, if I give you only the refund, for example, I give you another attribute, the same thing. If you give you, for example, the taxable income, so see what the most important thing here, whatever attribute you're going to give you, I'm still being able to use this information in order to perform the computation that we're looking for. So far, so good? Good. Let's try to see some problems. Of course, not. Remember, in this class, I give you like, let's say, I'm not going to say naive, but a simple, let's say, algorithm which help you to perform the computation based on this. Then we'll try to enhance this one. See, okay, it's like a naive approach. It's not to say efficient. There's some issues. Then we'll start looking at how can you fix, right? So, if I give you like the marital stats is going to be merit, okay? And they give you this data, right? What did you notice here? Look at this one. Now, when you try to perform this computation, I don't need to write the formula, right? The probability of y equal yes, given the x equal, let's say, the marital stats equal merit equal to what? The probability of what? Merit, given, let's say, the class table is yes. So this one, the probability of what? X, in this case, the marital stats equal merit, given the class label equal yes. If you look at this one, you see that the marital stats equal merit, that the class label equal yes is equal to 0. So in this case, there is a potential problem. It's not a problem 100%, but there is a potential problem. If we try to estimate the posterior probability with the result that I'm looking for, what the class label is going to be for the given test instance, okay, from the training data. If the class label or the class conditional, we call this one, by the way, the class conditional probability, if you remember last time, right? The probability of x given y, we call this one the class conditional probability. For one attribute equal to 0, the same case here happened to the marital stats equal merit, given the class table equal to yes. Then in this case, the overall posterior probability can be 0. This one, 0 multiply anything can be 0, right? What's going to be the whole class going to be vanished, it's going to disappear. Okay. What if, I've said potential problem, so I will show you that what if this one going to be, serious problem. What if we remove this, record number, the instance value is equal to 7. Let's remind you what's 7 here. I will remove this one here, okay? Assume that we don't have this training data. Oh, yeah, we can use that too. Exactly. Yeah, we can do. And that's great. That's what we're going to talk about in a few minutes. But you are right. Yeah. So in this case, let me give you the problem. what if both of them gonna be equal to 0? Which class is gonna be here? It's not tie, right? We're not gonna say, okay, randomly we're gonna choose one of them. No, we cannot, right? Exactly, you're right. Yes, it's gonna affect everyone. So what if we have, in this case, we remove one tuple here, or one instance, which causes that the probability in given instance, I will say, test instance, they're gonna give us 0 for the posterior, say, probability for both the classes gonna be equal to 0. So in this case, what they're gonna do as a solution? As you mentioned, we're gonna use something like Laplace, smooth method. Okay? So in order to do that, what we're gonna do is modify, the naive, Bayes, classifier, okay, to do the following here. So we're gonna have, or talk about to say, different estimates, okay, for the condition probability. I'm not gonna just using simple fraction. I'm not gonna say NC divided by N only, right? We're gonna have something else. So this is the original one, right? We have the probability xi equals c divided by given y, equal nc divided by n. If nc equal to 0, the whole thing can be 0, and the whole of the entire posterior, probability can be equal to 0. Okay. So what we're gonna do? We're gonna use Laplace estimate, or they're gonna be use the M estimate. Okay. So in this case, I'm gonna do something, change something, right? Just modify this one. Okay. So here you can have. I need to make sure that I'm not allowed to have the probability for any a class condition can be equal to 0. So in this case, I can say I keep NC plus 1 divided by N plus V, and V is gonna be the total number of attributes. Value that xi can take. What all the possible number of attributes or the unique values, okay, that specific attribute or the value of xi can take. If xi take 15 attributes, or values, in this case, n plus 15. Okay. Or you can use M estimate, which in this case you have what? If you have a categorical, data type, I can say NC plus M times P. M is going to be able to say here with hyperparameter for our confidence in P. P and P is going to be like the initial estimate of the probability xi equals C given C, known a prior. So I know to have some initial estimate value known before do this computation. Still, even doing that, we don't like the way that we have, assume that all the attributes or feature of X is going to be able to say independent. So in this case, we try to do what? What we can do better, even without doing, in the top of the, smoothing method, as we mentioned. This is another example. You can do this one for the practice, okay? And this is going to be good practice for the exam, okay? So if you, by the way, if you understand the material of this class, then you are fine. You didn't have a problem, okay? Good. Give you the training set, and you're gonna perform this computation. Then this is the class table. The test to say instance, and you try to classify this one. Then end up we have the mammals added. The class table for this data instance. Okay. Just summarize this method. Okay, it's nice. It's like perhaps to isolated noise points, handle missing value by ignoring the instance during the probability estimate calculation, perhaps to irrelevant, attributes, redundant and correlated, attributes will violate the class condition, assumptions. We have something like, in this case, which is still said, it's sometimes not unrealistic, right, to assume that all the features are going to be independent in order to try to perform, the cluster, or try to protect the cluster. We're going to look at the different techniques. It's called Bayesian, the belief network. And we're going to look at this one, just, give you an idea. There's another way which helps us in order to perform, the classification using, the Bayesian classifier.